Okay. First of all, thank you for giving me an opportunity to present our recent study. I'm Masayuki Yamaguchi from AJIAA from Taiwan. I'm currently a postdoc fellow after receiving my PhD from the University of Tokyo, Japan, 2 years ago. So my specialty is the morphology of the protoplanetary disk using radio interferometer such as ALMA. So at this workshop, I'm going to talk about my recent study on the detection of new disk substructure of EX Lupi using ALMA. The collaborator is Bob and Takami-san. Yeah, they are very good guys. So I think that most of the audience are curious to the FU ORIs, but I will talk about the FU, EX Ruby. So I think it would be interesting for you. Okay. First, let me briefly introduce the young eruptive star, as you all know. So one of the most interesting phenomena in the Roma's young stellar object is the episodic accretions outbursts, which are characterized by their sudden 1 to 6 magnitude optical brightening. So among them, the EXORs, the class of young eruptive star that exhibit the outbursts of short durations with an interval of several years. Also, several potential triggering mechanisms has been proposed. No. So no clear observational feature has been identified to explain the mechanism. So in the background, we target EX Lupi, which is known to be the archetype of the EXORs. So this object has a young stellar age of 2 million years and is an M-type star with a Rho mass star of 0.5 solar mass. And this object is one of the nearby the young eruptive star at a distance of 150 parsecs. So these raw figures shows that photometric monitoring of the EX Lupi in 20 years. And you can see that the multiple outbursts occurs randomly. The most recent event has been happened on the 2 years ago. Yeah. So, but it is generally accepted that this type of the outburst comes from the infalling materials in the inner rings. But we don't know what is going on. So, especially for the inner disk. So we studied to use high-resolution ALMA observations to reveal the disk substructure, especially for the EX Lupi. So in this background, we target the EX Lupi, as you know. So which is so in this slide, so I will briefly explain the setup ALMA observations. So in this studies, we used 2 observing frequencies, band 3 and band 4, and as only continuum observations to cover for 2 gigahertz wide spectral windows. So this observation does not include the line observations. This setup achieves the high spatial resolutions better than 0.1 arcsec corresponding to 15 AUs. So we note that so this observation were made before there are large outburst in 2022. Okay. So this is a result. Yeah. So as you can see, so this those 2 figures shows the dust continuum image in the band 4 on the left and the band 3 on the right. The central stellar marker shows the stellar position of the host stars as determined by the Gaia DR3 parallax. The band image band for image is more spatially resolved than the band 3 images. Okay, the most important things here is that we detect 3 prominent features, such as outer ring, lopsided inner ring, with respect to the star, and the dust tail candidate, which is only seen in the band for images. The ring is likely have a series of clamps along with the azimuthal directions. So you can see that the ring features between the 2 images are somewhat different from each other, especially for the northwest directions. This is probably because the band 3 image has a lower sensitivities compared to the band 4 images and cannot detect such a faint dust emission. The lopsided inner ring has a relatively higher emissions compared to the faint dust emissions, faint ring emissions. So this, the last one is the dust candidate and dust tail candidate, only seen in the band 4 image. The reason, why there is no dust tail in the band 3 image is still open question, but probably due to their dust properties depending on their observing frequencies. Okay, so in this slide, so we derived the disk geometries such as disk inclinations and position angles by using the higher sensitivity band for image. So here we used the output suite on the outer ring and derived the disk inclination. So this left panel shows the result of the LF suite on the image. So we found that this derived disk inclination of about 40 degrees is in reasonable agreement with the previous literatures, yes, by using the other telescopes. The right panel shows the reprojected image using the derived disk inclination and positioning angle. Interestingly, so we found that the center of the elliptical model has an offset, of the about 5 AU, from the position of the host star. Okay, so we show that the scattered image, obtained by the obtained with sphere at the VLT, also support the lopsided inner ring. The right panel shows the continuum image overlaid on the scattered image. And the scattered image shows the asymmetries with the intensity increasing the northwest directions. This asymmetry is consistent with our idea there's a vertically thick inner ring located southeast of the star, allows the stellar radiation to pass through in the northwest directions, but blocked in the southeast directions. So that way, so all of this strongly supports the existence of the inner lopsided disk surrounding the star. Okay. So in this slide, I present the disk size using the curve growth method to compare the disk size in the disk midpoint traced by the millimeter wavelengths and the surface traced by the scattered image. The left panel shows the azimuthally averaged radial intensity profile. The purple line is the profile of ALMA, while the orange line is the profile of the scattered image of the PLT. So you can see that the disk in the disk midplane is a compact disk with a radius of about 40 AU, while the disk size this surface extends to the radius of about 150 AU. It's 4 times larger than the disk midplane. Okay, so from this slide, let's focus on the lopsided inner ring. Okay, derived by ALMA. So this image has close-up view of the inner ring. So we derived a spectral index of the index into the 2 values from the 2 images, which suggests optical thickness even at the low observing frequencies of the band 3 and band 4. So as you can see, the inner rings in the current ALMA image are only marginally resolved at a spatial resolution of about 0.1 arcsec. So we need to get higher spatial resolution to further constrain the shape of the inner ring. Okay, so here is our strategies to overcome the limitation of the spatial resolution of the ALMA by using new imaging techniques with sparse modelings. So this is one of the techniques developed by researchers who aim to obtain high fidelity and high resolution images of the black hole shadows with the event horizon telescope. This technique can directly solve the incomplete sampling of the observable data by using the non-polarimetric imagings, which consist of the chi-square and 2 penalty terms. So if I was the invited speaker, I can fully explain these details, but so I will skip this one, sorry. So, okay, and we developed a new imaging software called Prisms. So this imaging takes place as a custom environment and has a computational time comparable to the accurate imagings. So in our studies, we use this software to improve the spatial resolutions. Okay, so before showing the EX Lupi, so I demonstrate that this application of the prism imagings. So this data is taken by the ALMA Band 6. And this gallery is taken is a 43 plot planetary disk in the Taurus Origa regions. Yeah, as you can see, thanks to these imaging techniques, the spatial resolution has been improved by a factor of 2. Yeah, this is the advantage of the imaging tools, yes, over the parametric imagings on the visibility domains. Okay, so this is the result. So as you can see there, so the result of the super resolution image of the EX Lupi with a spatial resolution of 40 millimeter arcsec corresponding to a scale of 6 AU. So our imaging techniques successfully constrain the shape of the inner rings. And you can see there are the candidate of the dust tail on the band 4. Yeah. Okay. So next, using these disk images, so we performed the projection using the disk geometries and converted them into the position angle profile as shown in the left panels. So top panel is a band 4 and band 3, and second is band 4. And the third one is ring width, yes. And the last is peak intensity profiles, which traces arc length. Okay. So, all right, so by using this measurement, we can get the elongation of the inner rings formulated by the aspect ratio of the arc length to the ring width. So we found that the inner rings is elongated more than 6 values. So which is similar to other lopsided disks around intermediate stellar objects, such as IRS-48 and AB Origa and HCD-1425-7. It's amazing. So most important things in this case, so these lopsided disks are often considered to be the product of the dynamical interaction between the companion and the disk. This provides this left figure shows the planet-disk interaction produce high contract dust asymmetries at the edge of the cavities. That way, so our findings of the lopsided reading in the EX Lupi maybe provide the tentative evidence of the presence of the planet very close to the star. Okay. So, okay. Okay. So, okay, so this is the summary of the result. Okay. So, okay, so maybe if you have time, let me discuss about the possibility of the episodic accretion in these planetary disk interactions. So the COSPAR, it was 2014, has previously argued that there is a multiple planet close to the stars by using the diurnal velocities. So by giving the disk inclination of the 40 degrees, so we estimate that this giant planet should be the 10 Jupiter mass. Yeah, it's very large. Yeah. So this comparison between our result and this radar velocity result. So we consider that so giant planet slow down their mass accretion to the star by accumulating a large amount of the material in the lopsided inner rings, eventually leading the accretion burst via radial flow from the inner rings. This is my argument. Okay. So that's all. Thank you for the attendance.
Okay, thank you very much. And let's encourage young people for a question or two. So, does anyone have any questions? Even, I mean, naive questions are also very welcome. Okay, go ahead. Thank you.
Hi, nice to talk. The very last slide where you talked about this planet, the existence of a planet with the radial velocity. The period of the radial velocity, and if you look at the light curve, they are showing exactly similar period. So like 7.4 days.
Yes.
Yes. So assuming your radial velocity giving to be coming from a companion, and the photometry, which has been consistent for last like almost 15 years, to be coming from the hotspot with the similar period. Don't they conflict from each other?
Maybe this is the candidate of the mechanism to occur this. Yeah, but I'm not sure in details. Yeah.
Okay, we will discuss.
Okay, let's discuss later.
Okay, any questions? Okay, please go ahead.
Thank you, Yamaguchi-san. Really exciting results. Not really a question, a comment. To encourage the audience, I think this is a very exciting result. The fact that where you think there is a planet is exactly where we, on the side of the disk that we found an asymmetry in the gas, in the band 6 data at 0.3 arcsecond resolution. The disk is conspicuous because on the east side of the disk is beautiful Keplerian pattern.
Yeah.
But if you see on the right side, there is this hourglass sort of morphology that is shifted from the center of the star.
Exactly. Yeah.
So the jury is still out on what is causing that. It would be great to see if there are modelers here in the audience, simulations of what would be the effect of a planet there on the kinematics of the overall disk, and see if that can reproduce what you're showing here on the band 6 ALMA data.
Thank you so much for the comment. Yeah.
Okay, quick question.
I'm puzzled by this offset between the stellar position and the central dust peak. So, considering that these are very long baseline observations, and then this central component has, I don't know how many signal to how significant the emission is, but considering all these, have you checked what is the basically the absolute astrometric calibration of ALMA? So how significant that offset between stellar position? So how sure are you that this is significant?
Yeah, so there are the positioning errors based on the ALMA technical books. So This positioning error mainly depend on the signal to noise ratios on the images. So we consider that this error of the offset between the stellar and peak position of the inner rings. So given that these signal to noise ratios, so this the positioning error can be small. It's very small rather than this offset between stellar position and peak positions. So we conclude that this offset should be reliable. This is my comment. Yeah.
Okay. Sorry, the time is running out. So yeah, please keep talking during any part of the session. Okay. Thanks again, Masayuki, and all the speakers in the morning. Then we